Welcome back. This is part 2 of the third year junior cycle Easter revision course. Now you had Jennifer for the first part and now you've got me for the next hour and a bit. So in this part of our Easter revision course, we're going to be covering two different topics, one from chemistry and one from physics. The first topic we're going to cover is on atomic structure. So what does the atom look like? How do you write electron configuration and that kind of thing? Then we'll have a look at physical world, one of the trickier topics, which is motion. So we'll look at how to calculate speed, acceleration, etc. So we'll be doing lots and lots and lots of practice questions. Now for this part, we're going to be starting with page 32 of your revision notes. Now the first part of the notes dealt with the biology section that Jennifer covered just before this. And now we're going to look at the chemical world section, which starts with structure of the atom. Now, these notes only cover a small snapshot of what the junior cycle notes are. So for this one, now for structure of the atom starting on page 32, when we're going through the notes, you'll notice on the top right-hand side of the screen, so up here, I've put a little grey box. So as I'm going through the notes, I don't like editing a PDF on the screen because I actually find it quite hard to follow when stuff is jumping all over the place. So instead, I've created slides for each one. Now, when you look on the top right-hand side of the screen, that's where you'll see the page that I'm on at that particular time. So on page 32, at the very top of the page, you'll see a grey box that looks like what you can see on the screen. These are the two learning outcomes that you have to be able to achieve by the end of this topic. Now, I know learning outcomes are a bit rubbish, but actually this is what the examiner is looking at when they're setting the exam. So they design the exam around these learning outcomes. So if we look at the first one, students should be able to describe and model the structure of the atom. So that's basically tell me where the subatomic particles are and what they are doing. So in terms of the nucleus, protons, neutrons, and electrons. So you need to know that protons and neutrons are in the nucleus and electrons go around the nucleus. And you should be able to compare mass, charge, etc. So now that's the first thing we're going to look at today. And the second part, students should be able to use the periodic table to predict the ratio of atoms of compounds of two elements. Now, this section is actually, it can be quite tricky for students to do. Even the Leaving Cert students don't particularly like this. So I'm going to show you the common ones that could be asked and we're just going to learn them. Okay, now as we're going through the notes, you'll notice that to keep you busy and make sure you actually get something out of this revision course, I've left gaps in the notes for you guys to fill in as we're working through it. Now, if you don't get something taken down, that's absolutely fine. These revision courses are being recorded as they're going out. So they will be available afterwards on the platform. So if you missed something and you're like, oh my God, what did she put in there? Or there's a big blank page or big gap on a page and like, what went in there? That's absolutely fine. You can just go back and rewatch it later on. So the most important thing that you're getting from this is that you're able to answer the learning outcomes, and everything else is just a bit of extra fluff and filler that we have. So starting off with what is an atom? Now, every piece of matter in the universe is made up of individual atoms. So as you're sitting in front of me now, you are made up of atoms of different elements. So an atom is the smallest particle of an element. Which still has the properties of that element. I'll explain what that means now in a second. Okay, so in chemistry, we have something called the periodic table. Now we'll see it later on because we'll be looking at it when we're trying to write formulas, etc. But the periodic table gives us a list of all of the elements that we know about or that have been discovered so far. And there's 118 of them. Now, luckily for junior cycle, we only really need to be able to deal with the first 20 or so. But it gives you a list of all of the known elements. Now, If I had, so say for example, I have a block of gold and it's pure gold. Now, that block of gold is made up of atoms, and the only thing that would be in there if it's pure gold would be just the atoms of gold itself. So if I was drawing a particle diagram for this, which you would have seen in a different topic, probably in states of matter, your particle diagram for a block of gold will look like this, because gold is a solid. Now, these particles that we use for gold or whatever the solid is, they are all individual atoms of gold. Now, if you have an element, all the atoms of that element are identical to each other. So from my diagram, you can see that this atom of gold is identical to this atom of gold, and it should be. And in a minute, we'll talk about comparing the atomic number and the mass number and all of that jazz. But the most important thing from this is when you are comparing atoms of different elements, they are completely different to each other in terms of size, electrons, protons, etc. So an atom of an element, so all the atoms of one element are identical and they are different to atoms of other elements. But basically, atoms are the building blocks of matter. So everything that you see in front of you is made up of individual atoms. And usually they're stuck together to form molecules, but we'll deal with that. Right, so next up is our subatomic particles. Now, this is the page that deals with the first learning outcome that we talked about at the start of this section. So this bit is really, really, really important. Now, you need to be able to fill in the charges and the relative mass for each of the following subatomic particles. Now, what does the word subatomic particle mean? So these are subatomic particles. So these are the particles that you find inside an atom. And there's three subatomic particles that we deal with at junior cycle. We have protons, electrons, and neutrons. Now, the way to remember this is, as you're looking at it, the word proton. So when you're trying to figure out what charge does it have, when you look at the beginning of this, you see the word pro. If you are pro something or something is pro, that means it is positive. So the relative charge on a proton is +1. Now, go down to the bottom one. We have neutron. Now, that's very similar to the word neutral. If something is neutral, that means it has no charge. And that's actually where the name of the neutron comes from. It comes from the word neutral. So a neutron in nature has no charge at all. Now, looking at the electron, this is the one that most people find the most difficult. Well, we know that which one is +1 and we know which one is 0. The electron has to be -1. Now, I've heard students do this in different ways. So some people do it as the E at the start of electron. That would be like writing the word negative. So E there for negative. Now, another way of doing it is just knowing or remembering that if you have a +1 and a minus, or a +1 and a 0, well, then the electron has to be the negative one. Now, so we have +1 for protons, -1 for electrons, and no charge or neutral for our neutrons. Now, for the relative mass, a proton, when we say what mass has it got, how heavy is it? How much stuff is it made up of? Well, to be honest, make things easier on us, we just say it has a mass of 1. Now, it's not 1 gram or anything like that. You don't need to worry about the units here. So we're just going to say a proton has a mass of 1. And so does a neutron. Neutrons and protons actually have the same mass. Now, the one that's always the more difficult one is the electron. Electrons are so much smaller than protons and neutrons. Now, their mass is 1/1835. Now, if you were to type that into your calculator, 1 divided by 1/1835, that gives me a decimal point of 0.0005. There we go. It is absolutely tiny in comparison to a proton and a neutron. And it is. Protons are nearly 2,000 times smaller. They're so small. Now, what do you need to remember from this table? You need to remember these numbers here. So be able to give me the relative charges for protons, electrons, and neutrons, and the mass. So now, you can come up with some way of remembering them, and I know it's usually the electron that causes the problems. The electron's mass is so small that it's negligible. That means it's unimportant. It's so tiny, it might as well be nothing, pretty much. Now, that is comparing our subatomic particles. And if you have this, you have most of the learning outcome that we looked at earlier on. Now, next up is we're going to look at how are these subatomic particles arranged inside an atom. So now in your notes, you have a space for drawing the diagram of an atom, and this is underneath where you wrote in your subatomic particles. Now there's a big box at the bottom of page 32. Now inside here, we're going to draw a diagram of an atom. Now we've got 3 subatomic particles to fill in. We have protons, electrons, and neutrons. Now, where they are is actually very important. Protons will be found in the nucleus. This is the very middle part of the atom, and so will neutrons. Remember, nucleus. Neutrons are in the nucleus as well. Now, electrons are a little bit different. These are found in the orbits or the shells, and they move around the nucleus. They're not found in the nucleus at all. So, if we're going to draw a diagram of the atom, we start off with the nucleus, so the very middle part of the atom. Now, inside the nucleus, we have our protons and we have the neutrons. Both of those particles, subatomic particles, are found in the nucleus. Now, based on that information, what charge does the nucleus of an atom have? Think about the subatomic particle that's in the nucleus. You have protons and neutrons. Now, overall, what charge does the nucleus have? The nucleus is going to be positive, and the reason for that is protons are positively charged and neutrons are neutral. They have no charge. So for that reason, the nucleus actually is positively charged. Now, your electrons, you'll find them going around the nucleus in these rings, like this. Terrible circle. Anyway, we're just going to go with it. Right, the first one we call n is equal to 1. This is the first shell around the nucleus. Now, when we start putting electrons into the atom, I'll show you how to draw or what the rules for this are in a minute. Your first electron is going to go into n is equal to 1, and so will the second. Now, the first shell, the first ring around the nucleus can't hold more than 2 electrons. It's a maximum of 2, and that's it. Then your other electrons go into n is equal to 2, and then you keep working out. And then you can have up to 8 in the second. You can have less than 8, that's absolutely fine, but it's a maximum of 8, etc. And that's what your atom looks like. Now, these electrons, I'm pairing them up to make them easier to count and see am I missing anything. But those electrons move around the nucleus, kind of like how planets orbit the sun. Another name for these shells is actually orbits, which we see that word later on if you do chemistry for the leave insert. Now, that is basically what a diagram of an atom looks like. In the very center, you have your nucleus. And inside the nucleus, you have protons and neutrons. And then you have shells that go around the nucleus, and this is where you find the electrons. Now, next up, we have to deal with what makes different elements different. Why are they different to each other? Why have we got 118 different elements? What's different about them? So first up, we're going to see the atomic number. Now, the atomic number of an element is a very unique number, and every single element in the periodic table has its own unique atomic number. Now, what does it mean for an atom? The atomic number is the number of protons in the nucleus. And every single element has its own unique number of protons in the nucleus. That's what differentiates each element from another one. So if we were to look at the element that you see on the screen, you can see the element fluorine. So capital F is fluorine. Now the atomic number on this is this number up here on the top. When you look at the two numbers that an element has in the periodic table, the smaller of the two numbers, that is the atomic number. So in this periodic table, your atomic number is there. So, what does this tell me about the element fluorine? This tells me that fluorine is the element, so capital F for fluorine. How many protons does fluorine have? Well, that's what the atomic number is telling me. This means we have 9 protons in the nucleus. Now, atoms are what we call atoms overall. When you've looked at all of the subatomic particles, they are neutral. So your number of protons must be the same as the number of electrons. So in a neutral atom, the word atom means you're dealing with something that has the same number of positives and the same number of negatives. We use a different word for something that's charged. We actually call it an ion. But the word atom, so if you see atom in an exam question, protons equals electrons. So this also tells me that fluorine has 9 electrons. There we go. So that number is actually giving you quite a lot of information about this particular element. Now let's look at another one. If I just move this up. Another element that you find in the periodic table is the element carbon. Carbon from the periodic table has an atomic number of 6. So remember, the smaller of the two numbers, that is the atomic number. So the element here, capital C, means carbon. Now, to be honest, you only really need to know the first 20 elements of the periodic table, so that if we give you the symbol, that you can identify what element that is. But if you're stuck, don't be panicking. These elements are all listed in alphabetical order at the back of your formula and tables books, which you get in the exam. So if you're like, oh my God, I can't remember the symbol for potassium, you just look it up at the end of your formula and tables book and you'll find the symbol there. The symbol is K, by the way, for potassium. So capital C is carbon. Now that's telling me that carbon has 6 protons in the nucleus. And because it's an atom, we would also have 6 electrons. But even if you were asked what is the atomic number of an element, you always tell me it's the number of protons in the nucleus. And we don't mention the word electrons in relation to the atomic number at all. So just be careful of that. Now, how is fluorine different to carbon? What makes these two elements different from each other is actually this number here. It's actually the atomic number. So every single element in the periodic table has a different number of protons in the nucleus. And that's actually how you identify what the element is. So if I was to give you this one, so I'm going to tell you not much about it. So we're going to look at another one. I'm going to tell you that an element is 8. We don't know what the identity is and we don't know what the mass number is. As soon as you see the number 8 here, that's giving you the atomic number of the element. So you just need to find element number 8 in the periodic table. So you would open up your formula and tables book and find element 8. This would be oxygen because it would be capital O. Now, how is oxygen different to carbon? Well, it has a different number of protons in the nucleus. The number of protons in the nucleus identifies the element, and you should be given it or information about it in the exam. Now, the mass number is different. Now, the mass number is the second number that you see when you're looking at the periodic table. This is the number of protons plus neutrons in the nucleus of an atom. So for fluorine, when we see this number here, the mass number is always the bigger of the two numbers. It has to be the bigger of the two numbers because you are adding two subatomic particles together. So the mass number for fluorine is 19, and this is the number of protons plus neutrons in an atom of fluorine. Now, based on fluorine, we saw up here the 9 on the previous slide was the atomic number. Now, the atomic number gives you the number of protons in the nucleus. Whereas down here, we have, so for this, we know that we have 9 protons. That means go down to the mass number, we know we have 9 protons because the protons aren't changing. It's still fluorine. How would I find the number of neutrons? So if you're asked to find the number of neutrons, what you need to do is, it's the mass number minus the atomic number. It's the difference between them. So for fluorine, if I wanted the number of neutrons, that would be 19 as the mass number minus the atomic number, which is the number on top, which is 9. 19 minus 9 is 10. Now, why do you need to be able to do this? Because you could be asked to list the number of subatomic particles. So based on the information that you see on the screen, we already know that we have 9 protons because the atomic number is 9. How many electrons would we have in an atom of fluorine? Well, the protons equals the electrons, so we also have 9 electrons. And now we have worked out the number of neutrons. You just subtract the two numbers together. So it's 19 minus 9, which gives me 10. Now, in the exam, you can get 3 marks for each of these that you can count, and it is important that you can count them. Now, this is our periodic table. So there's a picture of the periodic table in the middle of your formula and tables book, and you are given one of these in the exam. Now, you'll find this one on page 79 of your formula and tables books. So when you're given one of these books, you need to be able to figure out where you're looking for the information that you need. So we're looking at page 79. And if we look at each individual element, so if you look at lithium over here, lithium has an atomic number of 3. And if you compare that to beryllium, beryllium has an atomic number of 4. So every single element in the periodic table has its own unique number of protons in the nucleus, because that's what identifies what the element is. Now, you might be wondering why some of the mass numbers are decimals. It's actually due to isotopes, which we're not going to get into now. So don't worry about that. You'll be using whole numbers and they'll give them to you in the exam. Now, for silicon, let's do it one here. Silicon, from the periodic table, the number on top, the smaller of the two numbers, that is my atomic number, which gives me the number of protons in the nucleus. And my 28 is the mass number. So this is protons, and this is protons plus neutrons. So if we were to count the number of subatomic particles here, silicon has 14 protons in the nucleus. How many electrons have we got going around the nucleus? We have 14. And how many neutrons have we got? Now remember, for your neutrons, it's the big number minus the small number. That will be 28 minus 14, which is 14. So you have 14 each of the protons, electrons, and neutrons. Now, that's silicon. Now, for my worked example down at the bottom of page 33. So you can see that you've got a box down the bottom of the page where you see this question. It says, calculate the number of protons, electrons, and neutrons in an atom of carbon. And I haven't given you any more information than that. So what we would do here is we would actually go to the periodic table like this. and we find carbon. Now, carbon is over here. You see an atomic number of 12. Sorry, a mass. Said that the wrong way around because I was thinking you must remember to say the mass number. The atomic number is 6 and the mass number is 12.01. We're going to round that to 12. So here we write down carbon. You've got 6 as the number on top and 12 as the number on the bottom. Now, remember, your atomic number gives you the number of protons. So your atomic number is this one here. And the big number on the bottom, that is the mass number. So for counting my number of protons, there are 6 protons in an atom of carbon. Electrons will be the same as the number of protons, which will be 6. And how do we know that? When you see that word there asked in the exam, atoms are neutral. So you have to have the same number of positives and negatives. If you have 6 protons, 6 positives, you have to have 6 negatives as well. So 6 electrons. Then for my number of neutrons, that is the big number, 12, minus the little number, which is 6. That gives me 6 neutrons. And you get 3 marks for each of those. Oh, I actually put in a periodic table there. Go me. Now, next up is what is an isotope. Now, this is actually why we have decimals when you're looking at the mass number in the periodic table, because you use the same periodic table as the 6th years do, and they go into isotopes in a lot more detail than you guys do. These are atoms of the same element. Now, think about that for a second. If you were dealing with atoms of the same element, what makes them the same? So if something belongs to the same element, what does it have similar or that's the same as the other atoms? You have the same number of protons in the nucleus. But isotopes have different mass numbers. Now think about that for a second. Your atomic number that you see in the periodic table gives you the number of protons in the nucleus. The mass number that you see in the periodic table gives you the protons plus the neutrons. Now, if isotopes are atoms of the same element, they have to have the same number of protons. So what is different? So the protons have to be the same. So in order for them to have different mass numbers, what is different about what's inside the nucleus? They have a different number of neutrons. Now, we're not going to go too much into isotopes. You just need to be able to know a little bit about them, but not too much information. When it comes to isotopes, you might have heard of a very famous one, which is carbon 14. Now, when you see it written like this, the name of the element will be written first, and this number that you see after it, this is the mass number of that isotope. Now, it doesn't match the mass number that you see in the periodic table. If we go back here, carbon in the periodic table is here, and its mass number is 12.01. Now, the reason why the periodic table mass number is different is that is an average. It's an average of all of the isotopes of carbon, and there's actually 3 of them. Carbon 14 is the most famous of them because this one is involved in archaeology. You can use carbon 14 dating to figure out how old a skeleton is or how old a piece of paper is. And we study that in more detail when it comes to 6th year. Okay, so let's do this in relation to hydrogen. Hydrogen would be the nicer of the 3. Hydrogen has 3 isotopes. So there's 3 isotopes of hydrogen that you find in nature. Now, when you're looking at hydrogen as an element in nature, all 3 of these isotopes will be found. It's not like you only have one of them. All 3 of them will be found as atoms of hydrogen. You'll have a mixture of them. So the first one is this one. Now, from these numbers, the number on the top is telling you that you have one proton in the nucleus. So if I was drawing a diagram of this, I have one proton in the nucleus. Now, how many neutrons would I have? You'd have 1 minus 1, which is 0. This atom of hydrogen would have no neutrons in the nucleus. Now, it's an atom of hydrogen, so we have 1 electron. The number of electrons is the same as the number of protons. Now, that's the first isotope. The second isotope of hydrogen, it's still hydrogen, so the atomic number, the number up here, is still 1 because you still have 1 proton in the nucleus. But the number that's different is the number on the bottom. The mass number is different. So now, we still have 1 proton in the nucleus, but now look at the number of neutrons. Neutrons is this number minus this one. 2 minus 1 is equal to 1. So this isotope of hydrogen would have 1 neutron in the nucleus. Now, how many electrons would it have? It only has 1. And the third one is this one. Now again, you have an atomic number of 1. That means 1 proton in the nucleus. Now for my number of neutrons. 3 minus 1 is equal to 2. You would have 2 neutrons in the nucleus. And then you still have 1 electron going around the nucleus. Now, the only thing that's different about each of these atoms of hydrogen is this. It's the number of neutrons in the nucleus. And that's all we really need to know about isotopes. That's how they are different. They have different numbers of neutrons in the nucleus. That's it. Now, next up, I'm going to show you how to write the electron configuration of an atom. Now, this is quite important. So here, electrons are found in electron shells or orbits, which are arranged around the nucleus. So they go around the nucleus in these paths. The way in which an electron's atoms are arranged is called the electron configuration. It provides an address or a location for all of the elements or all of the electrons in an atom of an element. So it's basically telling you how many electrons you have in each of the rings around the nucleus. So we have a few rules that we need to follow when we are writing the electron configuration of an element. The first one, the first shell, the first ring around the nucleus can hold a maximum of 2 electrons. The second and third shells can hold a maximum of 8, and that's it. It can't hold more than 8. The second and third rings around the nucleus can have less than 8. So it's any number of electrons up to 8, but not more than 8. Now, the exam tip, the number of shells or the number of rings that you need to draw around the nucleus, you'll find that using the row number. So for example, in the periodic table, magnesium is in the 3rd row. So you go 1, 2, 3, and you find magnesium. So it's in the 3rd row down. That means when you're drawing an atom of magnesium, you need to draw 3 rings around the nucleus for the electron shells. Then the second tip, the number of electrons in the outer shell is equal to the group number. So that is the column. The groups are the vertical columns where you find your elements. Magnesium is in group 2, so you'll have 2 electrons in the outer shell. It's a way of checking, have you drawn the structure correctly? Next. So an example. Now on page 35 of your notes, let's go down and look at the worked example at the bottom of the page. Now this says, draw the Bohr structure. Now that's a fancy way of saying just draw an atom. So that's where you draw these rings around the nucleus and show me where the protons, etc. are. Now magnesium. Magnesium is the atom. So we have the same number of protons and electrons. And then we want to write the electron configuration. Now for this, I'm going to flick back and just go back to my periodic table. So apologies for jumping. I thought I put one in, but I did not. So here we go. Now magnesium is over here. Now look at the atomic number. My atomic number up here is 12, and the mass number we're going to use is 24. Now look where magnesium is. It's in 1, 2, 3. It's in the 3rd row of the periodic table. That means we need to draw in 3 rings around the nucleus, and it's in group 2. So we have 2 electrons in the outer shell. So when we're drawing this in, we start with the nucleus in the middle of the atom. Now, in the nucleus, I always draw in the number of protons and protons and neutrons. So we have 12 protons and 12 neutrons. Then in the first ring around the nucleus, we need to draw 3 because it's in the third row. Now, remember in the first one, the one that's closest to the nucleus, you can have a maximum of 2 electrons. Now, think about magnesium. How many electrons in total do we need to fill in? So the atomic number 12 gives you the number of protons in the nucleus. But because we're dealing with an atom of magnesium, the number of protons equals the number of electrons. So we need to fill in 12 electrons here. So we have 1, oh, apologies, that's not the first one. 1, 2. Now, when you put 2 electrons in the first shell, you're done. It can't hold more than that. But I still have more electrons to fill in. I still need to put in another 10. So what we do is we now move to the second shell around the nucleus. And we go 1, 2, 3, 4, 5, 6, 7, 8. Now at this stage, I have filled in 8 electrons in the second and 2 in the first. So I filled in a total of 10. But once you have 8 in the second shell, you can't put any more in there. So now we need to move to the third shell. And that's where the last 2 electrons go, in the third row. Now, to write the electron configuration, that's where you tell the examiner how many electrons are in each row. And you start from the first one, or in each shell. You start from the first one. How many electrons have we got in the first shell? We have 1, 2. So the number we write down is 2, comma. Now you move out and go to the second shell. How many electrons have you got? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons in the second. And now how many are in the third? You have 1, 2. So my electron configuration looks like this. If you have 3 shells around the nucleus with electrons in them, you should have 3 numbers written in. If you only have 2 shells with electrons, well, then there will only be 2 numbers. And you always start from the first shell, the one that's closest to the nucleus, and then you work your way out from there. Now for this, you get 3 marks for drawing the Bohr structure, or just the diagram of the atom, and then you get 3 marks for writing the electron configuration like that. Now that's it for atomic structure. We're completely finished here. So now your job, not now in the middle of the revision course, but still, to kind of help you practice what you have learned here, I want you to scan the QR code that you have in your notes, and that will give you access to PDFs of practice questions that I wrote for the main science notes. So they're practice questions for you guys to do later on. Now, at the end of that topic in your notes, you should see that you have a checklist like this. Now, this is basically, what do you need to know? So now, number 1, can I define what an atom is? It's the smallest particle of an element that can exist and still have the properties of that element. So if you can rattle that off, you would tick yes. If you're a little bit hazy, you kind of know what an atom is, then tick kind of, or no, that means that's something you need to go back and learn. Name the 3 subatomic particles, and then there's other checklist questions as well. So being able to give the number of protons, or the charges and the masses on your protons, neutrons, and electrons, etc. Right, that's it for our chemical world topic that I wanted to cover today. So now the next thing we're going to look at is the motion topic. Now motion is all about movement. So the main thing that we'll study here is speed and acceleration. So if you look at the learning outcome that's given on the page, this is covered on page 37 of your revision notes. So Physical World 2, it's the second learning outcome. Students should be able to identify and measure or calculate each of the following variables. Now the ones that you're going to study in this topic are speed and acceleration. The rest of them will be covered in different areas in the physics topic. Now, These definitions, so sometimes in the notes, I like to put a keyword box underneath the learning outcomes because it really helps to highlight what the important information is. So now, from each of these, you need to be able to tell me what it is, but also give me the SI unit, which you can see on the screen. And I've also put in the important formulas. So if you know this box really, really well, that actually is going to be a huge help in this topic and help you with calculating what you need to calculate for motion. So the first one, acceleration is the change in speed over time. That's it. That's your definition for what acceleration is. And the unit is meters per second squared. Sometimes when you see meters per second squared, you see it written like this, where they've taken the slash out of it and they put it to the -2. Those two things mean the same thing. They both mean meters per second squared. And it's important that you know what the unit is, because it's quite often on the exam they ask you what is the unit. To calculate acceleration, we have this formula here. Acceleration is the final velocity or speed minus the initial over the time. Now, we'll actually be looking at calculating acceleration with a few different examples in a few minutes. But basically, just before you go into your exam, this page is a really, really good one to look at and kind of refresh the key bits of information that you need for this topic. Now, displacement is the distance that an object travels in a certain direction. Displacement is very similar to distance. It's how far you have moved from your starting position. The motion, that just means movement. So this topic is called motion. So it's just talking about how things move. It's actually linked to forces, which is a different topic. Speed, it's the change in distance over time. Now, how is that different to acceleration? Acceleration is the change in speed over time. This is the change in distance over time. Now, the formula for calculating speed is this. It's your distance, speed, time triangle. Now, personally, I don't like writing stuff out that I don't have to. I'm a true chemist. Chemists are lazy. So we have distance, speed, and time like that. Now, why the triangle is useful is if I wanted to work out what the speed of something is, then I'm focusing over here on this side. It's the distance divided by the time. Now, the units are very important here. The unit for distance is meters per second. Now, it's not acceleration. Acceleration is meters per second squared, so just be careful there of the different units. Now, there's one other one at the bottom of the page. Velocity is very similar to speed, but it's speed in a particular direction. Now, a lot of scientists use the word speed and velocity interchangeably because if something is moving, it's moving in a particular direction. So we tend to use them to mean the same thing. Right, so the next thing we're going to look at is unit conversions. Now, this is something that comes up quite a lot in the exam. We need to be able to convert units of length because as you can see, your unit for speed was meters per second and the unit for acceleration is meters per second squared. That means when you're dealing with these two formulas, the distance that you are using has to be in meters. That's the one that's key. We need to be able to put the unit in meters. So we need to be able to go from centimeters to meters and kilometers to meters in order to work out these calculations. Now, to go from centimeters to meters, you multiply by 100. There we go. So if you have, no, you don't, apologies. As soon as I do this, every single time, you divide by 100. So if I have 120 centimeters and I want how many meters is that? Well, in that case, to go from centimeters to meters, you would divide by 100. 120 centimeters divided by 100 is 1.2 meters. There we go. Now, on the other side of that, to go from kilometers to meters, this is where you would you multiply every time. I've changed my diagram when I was doing this, so then I was like, oh yeah, I'll make it easier on myself. No. Kilo is 1,000. So you're multiplying by 1,000. If you have 10 kilometers and you want to convert that into meters, you would take your kilometers, multiply by 1,000, and then that will give you 10,000 meters. Just in case you have to do it later on. Right. Now let's look at our SI units for these different variables that you could be asked about in the exam. Distance, the SI unit for distance is meters. So that's what we're going to be dealing with in these. Displacement is the same. It's also meters. Displacement and distance are very similar. Distance is the total distance traveled. Displacement is how far you've gone from where you started. Time, your SI unit, is seconds, which has the symbol S. Speed, we have meters per second, and acceleration, we have meters per second squared. Now, it's very important that you learn the SI units for this table because it does come up in the exam where they ask you what is the unit. And you'll get 3 marks for each of these that you can name. If you get 15 marks for being able to give 5 units, I will cry with happiness because that's insane, but it's brilliant. Now, to calculate speed, so this is where we're going to start today. This is the most common one that you could be asked to calculate in the exam. So speed, we now know, is the change in distance over time. Now, looking at this is on page 38 of our notes. So again, if you're lost, this is the number up here that gives you the page number that we're dealing with in the notes. So speed is the change in distance over time, and the unit is meters per second. Now, if I want to calculate the speed, so this is the one that I want to calculate, we need to put the distance in meters and we divide it by the time. Now, personally, whenever you're answering a question where it asks you to calculate the speed, you always write the formula. Now, it doesn't have to look exactly like that. So let's look at the worked example. The worked example, let's highlight the important information. Now, it's important when you're doing calculations like this that you have a highlighter to hand because we want to try and extract the important information from the question. We don't want to be reading it 10 times to figure out what numbers are important because that's a waste of time. A boy takes 2 hours to travel from his home to the cinema, a distance of 10 kilometers. Calculate his average speed in kilometers per hour. Now in this one, it tells you to work out the speed in a particular unit. It's actually making my life an awful lot easier. Now, because the question has asked me to work out speed, so I'm calculating speed, the first thing I'm going to do is write my little triangle for calculating speed. So I've got speed down here, distance, and time. Now, I like triangles for calculating stuff in physics because it helps you to work out what you need to do. So what we do is we cover over speed with our finger, and that gives me the distance over the time. This line that you see here means divide. So to calculate the speed, that is the distance divided by the time. Now, if you look at the unit that they want this in, they want it in kilometers per hour. That means we need to put the distance in kilometers per, that's what that means. It means divide. And then the time has to be in hours. So based on the information in the question, the time is 2 hours. The distance is 10 kilometers. So we have distance and we have time. Now we can put the numbers in there. That is 10 kilometers divided by 2 hours is equal to 5 kilometers per hour. So it's kilometers per hour. That's what the divide means. It means per. Now, for this, it's quite common in the exam that you get marks for writing the formula like that. So you'll get 3 marks for your formula if you're really, really lucky, and then 3 marks for your final answer, including the unit. Now here, I only put it as 3 marks because sometimes you get marks for writing the formula and sometimes you don't. It kind of depends on the year. Now next, let's look at worked example number 2. Now you're supposed to be filling these in as we go. A man walked a distance, so the distance is 190 meters in 200 seconds. calculate his speed in meters per second. Now again, this is asking me to calculate speed. So before I do anything else, we write our triangle for calculating speed. Speed, distance, time, like that. Now we want speed, so speed is equal to the distance divided by the time. Now look at the unit for speed. It's in meters per second. That means the speed has, or the distance has to be in meters and the time has to be in seconds when we substitute in. So now, based on the information in the question, the distance is 190 meters and the time is 200 seconds. We have distance, we have time, now we can substitute in. So we have 190 meters divided by 200 seconds. And when we type that into a calculator, we get 0.95 meters per second. So he walks just under a meter every single second. And we get 3 marks for our final answer written like that. And hopefully you'd get 3 marks for writing the formula as well. It just depends on the question. Now, so as long as you have the distance traveled and how long it took to move that distance, you can always work out the speed, or even if it says the average speed, that's what it's looking for. So the next one. A car travels a distance of 27 kilometers in 22 minutes. Calculate the speed of the car in meters per second. Now, I'm highlighting the word speed because that's telling me what formula to write on my answer booklet. So again, I know I'm calculating speed. So we have my speed triangle, distance and time like that. Speed is equal to distance divided by time. Now look at your unit. It has to be in meters per second. So we need the distance to be in meters and we need the time to be in seconds. Now that's going to be a bit of an issue. So at the minute, the distance is 27 kilometers. We need this in meters. So how do we go from kilometers to meters? We multiply by 1,000. That will give me 27,000 meters. And that's the number that we fill in on top here for the distance. Now we need the time. At the minute, it's 22 minutes, but we need the time to be in seconds. So we need to convert from minutes to seconds. So what we do is, how many seconds are there in a minute? There's 60 seconds. So we take our minutes and we multiply it by 60. And that's going to give me 1,320 seconds. So let me double check that on my calculator. Yes. Now we have our time in seconds, so we fill in 1320 seconds. Now double check your units. You have meters per second, so you're fine with your units. Now we go to the calculator and work out our speed. So we have 27,000 divided by 1,320 and we get 20.4545 recurring meters per second. And we get 3 marks for working out that, and you're probably going to get another 3 marks for writing in your formula as well. Now, it's always important when you're doing this, always put the unit in. They are quite picky on that, so make sure the unit is there. Now, worked example number 4. This is going to be our last one for speed. So next up, a train travels at a speed of 120 meters per second. So that is the speed of the train. What distance has the train traveled in 2 hours? Now ask yourself, what is the question giving me? It's giving me the speed, it has mentioned distance, and we have the time. Now, that means you're going to be using your speed triangle because they are the 3 variables from the speed triangle, like this. Now, what are we asked to find? We're asked to find the distance. Now, cover over D on the triangle, so that means you need to take the speed and multiply it by the time. So your distance is equal to speed multiplied by time. So based on the information, the speed is 120 meters per second. The time is 2 hours. Now, we're going to have a problem here. If I was to come along and substitute in here, I have 120 meters per second multiplied by 2 hours. Can anyone see a problem with that? The units for time are not the same. Because the speed is given in meters per second, we also have to include the time in seconds. So our 2 hours that we have over here for time, we need to convert that into seconds. So we multiply, we have 60 seconds in a minute and 60 minutes in an hour. So we multiply 2 hours by 60 and then you multiply it by 60 again. So that gives me 7,200 seconds. To go from seconds to minutes and then minutes to hours. We're going the opposite way. We're going hours to minutes. So we multiply by 60 and then to go back again, you times by 60 again. So that's why I'm multiplying by 60 twice, because we're moving 2 steps on the conversion. So now we have our numbers to substitute in here. I have 120 meters per second multiplied by 7,200 seconds. When you multiply those together, we get a very big number, 864,000. Now look what happens to the units. We have meters dot seconds over seconds. What happens to the seconds? They cancel. And that leaves me with units of meters for distance, which is fine. So for this one, we get 3 marks for working out my distance traveled by the train. That would be a very, 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 very big difference. That's going super fast. Oh well, there we go. Now next, let's talk about velocity. Now for velocity, velocity is not the same as speed. Not quite the same, because speed is how fast something is going, but velocity is how fast something is going, but it is in a particular direction. So velocity has direction, and it has the same unit as speed, which is meters per second. Displacement down at the bottom is how far something has moved from its starting position. And I have an example in a second that shows you the difference between distance and displacement. So if I draw this diagram down here at the bottom, so say for example, we are starting here. We'll call this A. Now, A is the starting position. So someone starts off at A and they go for a walk through the forest. And they end up on this side of the car park over here. And we'll call this the end. Now, that white wiggly line that you see, if you were to start at the beginning and work out how long that squiggly line is, that is the distance. It's the total distance that that person has walked from point A to point B. Displacement is different. Displacement is how far they are from where they started. Their displacement is actually that. So an easier way of doing this would be if we have point A. So a person started walking from point A, they walked in a straight line to point B. To go from A to B, the person walked 20 meters. Now this person is walking in a straight line. So the distance that they have traveled is 20 meters. How far is that person when they're in point B from where they started? The displacement is also 20 because they walked in a straight line from that point to point B. If that person then walked back the way from B to A, what is the total distance that they traveled when they went A to B, back to A again? What's the total distance that they have covered? Well, they've covered 20 to get from A to B and another 20 to get from B back to A. So they've traveled a total of 40 meters. But now look at what is the total displacement. If they are standing back at A, how far are they from where they started? They're back where they started, so their displacement is 0. And that's where distance and displacement are not quite the same thing. Displacement is always looking at how far you are from where you started moving. Now, we've already talked about that. So what's the difference between speed and velocity? Speed is just a generic word for how fast something is moving. Velocity is how fast it's moving, but it gives you what direction, whether it's moving north, northeast, whatever. So it has direction, and for that reason we call it a vector quantity. It has size, meaning it has a number, but it's also in a particular direction. And this is where scientists kind of get ourselves into trouble a little bit, because we kind of use the words speed and velocity interchangeably, and it does cause a little bit of confusion. But for the purposes of what you'll see for Leaving Cert or for Junior Cert, you can kind of think of them as the same thing. Because honestly, if something is moving and it has speed, it has to be moving in a particular direction, at least at this point. Right, so with the worked example that we have at the bottom of page 41 is this. So it's very similar to the one that I just did on displacement a second ago. Using the line, answer the questions below. A man travelled from point A to point B. So he starts here and he ends up here, as shown in the diagram. Calculate the distance, the total distance travelled by the man. Well, if he starts off at A and he moves from A to B, he is moving 500 meters. So we're going to write in 500 and then we write small m, meaning meters. Question B. If the man travelled from points A to B and then back to point A, calculate the total distance travelled by the man. So A to B is 500 meters, and then B back to A is another 500 meters. That means he travelled a total of 1,000 meters, because it's the total distance that he moved. If the man travelled from points A to B and then back to A, calculate his total displacement. Now, if he is in the same place that he started from, what would his displacement be? It's going to be 0. Why? Because he's right back where he started. So he has to be a 0 displacement, because he started in the same place and ended up in the same place. Next, now let's talk about acceleration. This is the nasty one. This is on page 42 of your notes. Acceleration is the change in speed over time, and the units for acceleration are meters per second squared. This bit is important here, so I need you to highlight this bit in the notes. If something travels from rest, its initial speed, because it wasn't moving, is 0 meters per second. Now that's important, because when you're dealing with acceleration questions, if you see the word rest, then you know the initial speed is 0 meters per second. And it might not tell you it's 0, but because the word rest will be given in the question, you know that it is going to be 0 meters per second. Why? Because the object was not moving. If an object speeds up, then it is accelerating. If an object slows down, it is decelerating. So that's like when you're driving along in a car or on a bike and you hit the brakes. You slow down. That's called deceleration. The velocity or speed has to change for an object to accelerate, because you are traveling along at a constant speed, and then if you want to go faster, you have to accelerate. So they do go hand in hand. You can't just jump from one speed to another. You accelerate in between. If the velocity, now this is important, if the velocity is constant, so they're moving with a constant speed in a particular direction, the object is not accelerating. Because if you're moving with the same speed, acceleration looks at the change in speed. If you're moving with the same speed, you're not changing speed. So the acceleration has to be 0. Now, the formula for working out acceleration. It's the final speed minus the speed at the start divided by the time it took to get from one to the other. Now, I tried to do this as a formula before and it just ended up confusing the bejesus out of everyone. So, when something is accelerating, you start from an initial speed. It's what you start from. Speed or velocity if you prefer. And then you get up to a final speed after you have finished accelerating. And that's what this is looking at. It's looking at the difference, the change in the speed. That's why you're subtracting them. and then you look at how long it took to get from the initial to the final speed. So that's why it's over time. Now, let's have a look. Worked example number 1. Now, this one, I left a blank space so that you can fill in your workings as we go through this. Now, again, we're going to have a trusty highlighter to hand to highlight the key pieces of information here. A car travels from rest. Now, if something is starting from rest, what speed is it? If something is at rest, it's not moving. So if it's not moving, what speed does it have? That means we're dealing with 0 meters per second. And reaches a speed of 17 meters per second in 5 seconds. So we have the initial speed, we have the final speed, it starts at 0, it ends at 17, and the time is 5 seconds. And it says calculate the acceleration. So the first thing we do is we write out our formula. We always write the formula in these questions. Acceleration is the final speed minus the initial speed divided by the time. So now we look for those numbers in the question. The final speed was 17 meters per second. Minus the initial speed is 0 meters per second. And how long did that take? It took 5 seconds. So that would be 17 minus 0 divided by 5 is 3.4 meters per second squared. Okay? Now, it's important that you put in the unit, and remember we are working out acceleration, and straight away your acceleration is meters per second squared. I wouldn't really be bothered with working out the units here, just put in the units as meters per second squared. Now, worked example number 2. We're just going to do this one. A train accelerates from 31 meters per second. Now, what is that? That is the initial speed. That is what it is starting from. And it reaches a speed of 43 meters per second. So that is my final speed after 50 seconds. That is my time. Calculate the acceleration of the train. So we're going to find this out in meters per second squared. Right, so my first step is to write in my formula. We always write the formula. So we have final speed minus the initial speed divided by the time. Now, have we got a number for the final speed? We do. That's this number here. So we have 43 meters per second minus the initial speed over here of 31 meters per second divided by the time it took, which was 50 seconds. Come along and we type that into our calculator, and we're going to get 0.24 meters per second squared. And that's my final answer. Now, you'll notice that the 2 examples for acceleration, we're getting positive numbers, because when you work out acceleration, you always get a positive number. But in the next one, this is deceleration, so we're slowing down. And in this case, we're not going to get a positive number, but we're not going to panic. So let's write it in. A train decelerates from 20 meters per second. So that is my initial speed. That's what it was at the start. And reaches a speed of 13 meters per second after 12 seconds. So the 13 meters per second is the final, and the time is 12 seconds. Calculate the deceleration of the train. So again, we're going to write in the acceleration formula is the final speed minus the initial speed divided by the time. Now, write in your final speed, that's 13 meters per second, minus the initial, which was 20 meters per second, divided by the time, which was 12 seconds. Now, when you type that into your calculator, it works out as minus 0.58 meters per second squared. Now, the sign is actually important here. So when you end up with a negative number, that means we are dealing with deceleration, that the car or whatever it is slowing down, and that's why it is negative. Whereas when you have acceleration, where it's getting faster, you will have a positive number for acceleration. And that's just something important to note. So that if you end up with a negative number, it's not wrong. It just means that you have deceleration instead of acceleration. So don't second guess yourself. If you spend ages working out the acceleration here and you get a negative number, just leave it alone. And see, was there information in the question that's telling you that it is slowing down? And if it did, you're absolutely fine. Now let's talk about the motion graphs, just to kind of round off today's class in the last 5 minutes. I've skipped over worked example 4, but it's the same as the notes which are on the website. Now, you could be given motion graphs and asked, what is this motion graph telling you about how something is moving? Now, I used to do this with my second years, or even I did it with the third years at the start of the year, where I would print out a set of motion graphs for them, and we'd go to the PE hall and be like, right, tell me what the graphs are doing, and they had to act it out. So they had to move with how the motion graphs were showing them. It was actually great crack. It was one of the few ways you can make physics fun. Physics teachers will kill me for that, but anyway. So now this one, let's look at our units. We have distance on the y-axis and we have time on the x-axis. Now, it's important when you're dealing with motion graphs that you actually look at what the axes are telling you. So we have distance and we have time. When you see a straight line like this, where they look directly proportional, so as the distance increases, the time is increasing in the same way. This means that whatever the object is, it's moving at a constant speed. And that's important. So distance versus time and straight line through the origin. Your substance is moving at a constant speed. Now the next one, where you have distance on the y-axis and time on the x-axis. Now look at what the graph is telling you. The distance is not changing. So that would be like me going out into the middle of the sports hall, starting a stopwatch and not moving. So when you see that flat line, when you have distance on the y-axis, that means whatever it is, whatever the object is not moving at all. Okay? So this one, the one before it, it's moving at a constant speed. And this one, the object is not moving at all. It is standing still. And you can tell that because the distance is not changing. And why does distance not change? It doesn't change if you're not moving. Now, this one is a little bit different. Now, this one, look at the unit or what's on the axes. You have speed versus time. Now, this one is different. So when you've got speed versus time, like this is where your substance is moving with constant acceleration. The speed is constantly increasing over time. Now that is, to me, I honestly find that one the most difficult to spot. And the trap that the examiner sets you is speed. Now, what is the graph telling you here? That as time goes on, the speed is constantly getting faster and faster and faster and faster. It is constantly accelerating with the same pace. Now, another hint is when you see speed on the y-axis versus time, what variable have we been looking at today that compares speed or the change in speed over time? So when you see speed on the y-axis and time on the x-axis, this graph is telling you about the acceleration of the object. And instead of speed, it might give you the velocity, which is speed in a particular direction. So always watch out for ones like that. If you have speed or velocity on the y-axis, that's giving you information on the acceleration of the object. Whereas previously, when you have distance and time, what links distance and time together is speed or velocity. Now this last one, so these three, you should be able to identify what these are telling you. So on the y-axis for each of them, we have velocity versus time. Now, when you have speed or velocity versus time, what is that giving you information on? It's giving you information on acceleration. Now, the first one, that is moving with a constant, or yes, with constant acceleration, because we just saw that one. The second one, this is decelerating because the velocity is decreasing per unit time. So your speed or your velocity is decreasing, whereas this one, your speed is increasing because you're accelerating. And the one over here, when you have this situation here where your velocity is remaining constant over time, this is actually moving. Now, the velocity, as long as that line is above 0, then the object has to be moving. And the object is moving with constant speed. Now, how is that different to the graph I showed you at the very beginning? At the very beginning, we had a graph with distance versus time as a straight line like that. The graph on the top and the graph here are not the same thing. So look at what the y-axis is telling you. In the bottom one, it's telling you the distance is not changing. So imagine yourself sitting in the middle of the sports hall. How do I show this? I need to keep the same distance and start my stopwatch. So you just start the stopwatch and your distance is not changing. Therefore, you're not moving. So in this one, when it's distance versus time, it is not moving. But now look at the top graph. Your velocity on the y-axis, the velocity is remaining constant. So the speed is remaining constant. And because it is not 0, it is actually moving. So that's why we have constant speed for the top one, whereas the bottom one, it's not moving. And it's important when you get graphs like this that you read what's on the y-axis, because that tells you whether you're looking at constant speed or it's not moving at all. Technically, that's that one down here. It is moving with constant speed. You're just not moving at all, which is technically moving with constant speed. Your speed would just be 0 because you're at rest. So this is where we're at rest. Now, that is it. God, that was really quick. Now, to round out today's class, so we've done atomic structure and we have done motion. Now, to be honest with you, I know motion is hard. Everybody hates motion. It's like when you do circuits for the first time. They're nasty as well. So for these, I recommend that you do the practice questions where you can see the QR codes on the screen. These are the same QR codes from the revision notes and also the same QR codes from the main notes that I wrote for the science topics. So these QR codes will bring you to a PDF and have a go at the practice questions and see how you get on. The answers for what you're doing, if you're struggling with one of the calculations, then go back and check the worked examples in the main notes and see if they can help you. But the main thing is to write the formula on your answer booklet first and then see if you can figure out what numbers go where in your formula. Right, so that is it for our Easter revision course. Hopefully you picked up a couple of handy new ways of doing stuff or some tricks or tips that you didn't have before. And I'll see you guys soon.